Our next shapes to look at are the pointy ones, so pyramids and cones. Again, hopefully you've learned about these before, and this is all mostly just review stuff. It shouldn't really be anything new that you haven't learned before, just refreshing and then maybe doing a little more complex math with it, but it's all old stuff. So a pyramid has one base, as opposed to the shapes that we did in the last section, which have two bases, and it has an apex point. So it has one base, and then as opposed to the other one being extruded to a second base, it's extruded up to an apex point where they all meet. So what that means is that the sides are triangles instead of rectangles. So sides are triangles. A regular pyramid is one that has a regular polygon base. So if the base is regular, then the pyramid is regular. And then slant height is the height of the lateral face, so the height of the triangles. Height of the triangles, or altitude of the triangles, if you want to think of it that way. So a regular pyramid also needs not only a regular base, but it needs the apex to be directly above the center of the base. So kind of like in the last shapes with the rectangular shapes, we had a right shape or an oblique shape. So here we're not going to have an oblique pyramid because that would change all of the triangles. Like we wouldn't have identical sides anymore, and that would make it so that we can't really calculate anything for that shape in a reasonable way. So yeah, like we only have right pyramids. We don't have oblique pyramids. And then I guess this is, I put an irregular pyramid has no slant height. So slant height is relying on the height of that triangle. And if all the triangles aren't the same, then you're not going to have a uniform slant height. So most of what we're doing is going to be based around regular shapes, or at least right pyramids. So remember, right pyramid is talking about the angle here, that the altitude or the segment connecting the centroid of the base to the apex is going to be perpendicular to the base. So our formula for finding surface area, again, I don't really love formulas. The idea of total surface area is just adding up all the surfaces. So one of our surfaces is the base. So we use B to represent the area of the base. All of our lateral faces are triangles, and we know that triangles are 1/2 of their base times their height. And even though they're slanty, the slant height, we said, is the height of the triangles. So it's going to be 1/2 times each side times the slant height. But to kind of compact that down, we can say it's 1/2 times the perimeter times the slant height. So we could find each triangle individually, like I was talking about for the prisms, but in this case, I think it's simplest just to think of it as being the total of the 4 triangles. But if you want to add up the 4 separately, feel free. You'll get the same result, because that's all we're doing is adding up those individual 5 shapes in this case. Not always 5. Yeah, so right pyramid, we have a problem here where we're going to say the base is 5 by something. I assume this must be a square. If this isn't a square, but it doesn't say it's a regular. How would we know? Wait, what? How are we going to solve this if we don't know how wide the pyramid is? I don't see any way to approach this other than assuming this is a square. But they say right pyramid, not regular pyramid. So let's actually just make up our own numbers and say that this is 4 feet wide. So our base is 5 by 4. And that's going to be a problem because then we don't have a slant height. Not sure what to do with that, honestly. Yeah, I don't know. So I'm going to take it at its word, and we're going to work through this problem as if it is a rectangular pyramid, not a square pyramid, which means it is a much more complicated problem. So let's look at this regular pyramid first to see the difference. Maybe this will be a chance for us to compare and contrast how easy it is to do a regular pyramid versus a non-regular pyramid. So this formula is for regular pyramids, right? Okay, so regular pyramid is the area of the base. So my base area here is just 9 squared. And my lateral surface area is going to be 1/2 times the perimeter of the base times the slant height. And those are all given. So that's 1/2 times 4 times 9. So 9 times 4 is my perimeter. And my slant height is 13. So 1/2 and 4 becomes a 2. So I have 26 times 9. That's 180, and 54 is 234. And this is 81. So if I add them up, my total surface area is 81 plus 234, which is 315, and my units would be square meters because I'm measuring a area. Okay, so that's really easy, right? Just base in that. This is going to be harder because, as we said right here, an irregular pyramid has no slant height. So we need to, instead of finding a simple formula like this, start off with the base. Base is simple, so that's length times width, so that's 20 square feet. Real simple. Then we actually know the slant height, or the height of the left and right face, if we're thinking of that as a triangle. So this is the left, and the right is going to be 1/2 times, and again, we're just thinking about this triangle right here. Sorry, this right side or this left side. And its base is 5, and its height is this 4 right here. So those were actually pretty easy. And there's 2 of those, so I'm going to do times 2 and cancel out that 1/2. So our left and right area is 20 square feet. So that was pretty easy too. The challenge is going to come in with these front and back faces. So what we need is the height of this triangle along this slanted face. Now, let's see, how are we going to figure that? We know that this triangle is 2 feet wide right here. And we know, let's see. All right, so I think this is a several step process. So again, showing why this is going to be so much worse. So let's look at this triangle that's drawn in the middle. It's 2 across the base and 4 on the slant, meaning that this is a 30, 60, 90 right triangle because we see S and 2S, meaning the height of the pyramid. So I'm going to put that here. H of the pyramid is equal to 2 times the square root of 3 feet. Okay, so now we have a triangle that basically is the height of the pyramid, then coming out this way at a right angle, so perpendicular to that, and then the slant height. Those are all lined up here together, so it's hard to see them. So thinking about turning this to the side, so I'm turning this 90 degrees, and what we're looking at is this is 2 root 3 is the height. Then this line here going from the center out to the front face here is going to be 2.5 feet because it's half of this 5. And then what we're looking for is this missing slant height of the front and back face. That's what we need to find this last thing. So front and back is 2 times 1/2, because there's 2 of them, that cancels, times the base of that triangle, which is 4, times the height of that triangle. And that's the whole difficulty here, is finding that slanted height, which I'm calling x right here. So to find it, we would need Pythagorean theorem, and we would say x equals the square root of 2 root 3 squared plus, let's make it a fraction and make it 5/2 squared. Okay, so let's try to simplify that. 2 root 3 squared is 12 plus 25/4. So that gives us, if we convert those both into fourths, that's 48 plus 25 is 73/4. So this x is square root of 73/4. But at least that 4 part is a perfect square. So we could call that square root of 73/2 and get that out of the radical. Cool. So this 4 and this 2 become a 2. So we get 2 root 73 square feet. That's the total for the front and the back face. Now if we add these up, we get 20 plus 20. That's 40 plus 2 square root of 73. And that's in square feet. I think we definitely should get an approximation for that. So let's look at the calculator and do 40 plus 2 square root 73. So it says that's about 57. It actually works out to a pretty nice number, about 57.1 square feet. Now, I don't know if that was the intent of the notes, was for us to do that without it being a regular pyramid. Typically, we deal with regular pyramids. You saw how much simpler it was to be able to use 1/2 times the perimeter times the slant height, that all the faces had the same slant height. The main difference here is we had 2 different slant heights. We had 4 feet for the left and right, and for the front and back, we had this square root of 73/2 slant height, which was super awkward. So we can solve a problem like this. It's not a big deal. It's just more fundamental going to add up each face instead of being able to use a formula. So yeah, we can do it. All right, so moving on from pyramids to cones. Cones are like the equivalent for circles, like cylinders are to prisms, cones are to pyramids. So a cone has a circular base, so one circle base, and an apex point. Same kind of idea as it was for the pyramid. A right cone is the same idea, where the center of the circle to the apex, so center to apex, is perpendicular to the base. And then our slant height is the same idea as it was here. It's just not on a triangle. It's the height of along the edge of the cone. I don't know how to describe that other than that, so you get the idea. We can still find that slant height with the idea of a right triangle, though, because if we slice through a cone with a plane, it makes a triangle. So here we have a slant height of 8, so that's L, and we have a radius of 6. And our formula is, I don't even know what I would do with a cone that was, well, a right cone is a regular cone, so that's weird that they even distinguish that here. It's very odd. Because an oblique cone would not be a right cone, so I don't know. So this formula for regular cones is very similar to the one above. So we have the area of our base, that's the circle, plus we have the area of, or we have 1/2 the perimeter times the slant height. So it's basically the exact same formula because we're basing it on perimeter, and just this one has a circular perimeter, and this one had a polygon perimeter. All right, so both of these are going to be this simple formula. We're not going to have anything complicated like on the last one. So we have a slant height of 8 and a radius of 6. So our base area is pi times r squared plus 1/2. Our perimeter is 2 pi r. And then our slant height is 8. So simplifying, 1/2 and 2 cancel out. So we get 36 pi is the circle, plus the outer cone part is 48 pi. So our total surface area is going to be 84 pi square centimeters. So pretty easy, just like the regular pyramids are. And again, that's mostly what you can expect to see. This was just a more complex example we went through. Second cone, this one we still have the slant height and we have a diameter. So our area of our base is pi d squared over 4. Or you can change it to a radius and do pi r squared, of course. Plus 1/2 times our perimeter, which is 2 pi, pi d since we're working with diameter. So times pi times 20. Pi d times slant height, which is 15. All right, so here I'm going to make that a 5. So we have 100 pi is the circular part, plus the cone part, the outer part of the cone, is, this simplifies to 10, so we get 150 pi. So we in total have 250 pi, and that's going to be in square meters. So that's pretty much what there is to surface area. The same formula that you've seen before in math is the same formula we're using here, and it's a pretty simple one. It's just the idea of adding up those areas. Volume, you've also seen before, I believe. Volume also has a pretty simple formula for regular pyramids or for cones, and it's based on 1/3 instead of 1/2. So this formula is going to be 1/3 the area of the base times the height. And this will be the same for cones or pyramids, which is part of why they're grouped together. They're very similar shapes, just polygon base versus circular base, but they function in the same way. So the one new thing here again is that we now know how to find regular polygon areas, so you may have to bring that into play. It actually looks like we might need that here. So we know our height is 8 inches for this hexagonal pyramid. So we know that we have 1/3 times 8, and then we need the area of this hexagon. And it's a regular hexagon. We know the radius of it. So we're going to need to find the area based on that radius and the number of sides. So we know n is 6 and the radius is 4. So I'm going to redraw that hexagon separately, and hopefully that will help us. You know what? I'm going to have it help me draw this hexagon so I get a nice hexagon. Ink to shape. Perfect. Okay, so we have our regular hexagon, which I could have drawn a bit bigger, and we have the radius. We don't have the apothem or the side length, but we do know that a hexagon has 180 times 6 minus 2 over 6. That's 30 times 4. So each corner angle in a regular hexagon is 120 degrees. So that means our corner angle here is 60 degrees. That's pretty nice because that means we have a 30, 60, 90 triangle. So if our radius is 4, then we know that our side length is also 4 because each half of this side was 2. And remember, our area formula is ANS over 2. Now we know the number of sides is 6, the side length is 4, all we need is our apothem, which is going to be, so we know that it's going to be 2 times the square root of 3, because my S here is, or my S on my little right triangle, let's draw the right triangle separate. Okay, so we had 4, and this was my 60 degree angle and my 30 degree angle, so this was 2, and this was 2 root 3, because it's a 30, 60, 90 special right triangle. We know that relationship. So my area of my hexagonal base is going to be my apothem, 2 root 3, times my number of sides, 6, times my side length, 4, all divided by 2. All right, what can we simplify? So we have 2 over 2. Let's knock that out. We have 1/3 and 6. That simplifies to 2. So I'm left with 8 times 4 times 2. That's 64 square root of 3. So 64 root 3, and I'm doing volume now. So this is going to be in cubic inches. And that's going to be my exact answer. We could also do a decimal approximation, but we'll just move forward so we can finish up the notes. Volume of cones, same exact thing. So we have 1/3 times the base. My base is going to be pi r squared. And then times my height. I don't have my height. I have a slant height, but I do see a Pythagorean triple. This is a 6, 8, 10, because that's 3, 4, 5 times 2. So my height is 8. Let's split this out and put the 2 6s separately. That way we can simplify. 6 divided by 3 is 2. 8 times 6 is 48, times 2 is 96. So we get 96 pi, and we have no units. So just to make sure we remember, volume, though, is going to be in cubic units. So whatever the units were, we need them to be cubes in order to work for this. All right, so then you have some practice to do. It's basically just utilizing those two formulas. I would recommend that for these decimals like 0.42 that you do go ahead and round those instead of finding a precise answer. But if you'd like to find a precise answer, feel free. So do the practice on these for surface area and volume. Again, should be all recap. The only new thing would be these composite shapes where you're either subtracting a pyramid from a prism or adding a cylinder and a cone or things like that.